this video, countability of sets. I explained in the previous video what is when we say that set is countable. Countable means first we define what is denumerable set. What is denumerable? When do you say that set A is denumerable? A is denumerable means if A is equivalent to n set of naturals, we say that A is denumerable. Countable means if a set capital A is either finite or denumerable, then it is called countable set. Either finite or denumerable, then it is called countable set. Now, in this video, I prove some theorems, 2-3 theorems, and they are very important because you can take that as property of countable sets. And first theorem is every subset of countable set is countable. Proof is like this: every subset of countable set is countable. Now, what is countable set? Countable means either finite or denumerable. That means countable means either countably finite or countably infinite. Countably infinite is called denumerable. Now, therefore, two cases arises. Countable means either finite or denumerable. That is the definition of countable set. Either finite or denumerable. That is the meaning of countable. Now, therefore, I take two cases here. Proof has two cases. Let capital AB. What you have to prove? Every subset of a countable set is countable. Now, let capital A be countable set. Countable set. And B be a subset of A. Subset of A. Case 1 is like this. If capital A is finite, then countable means either finite or denumerable. That is called countable. So first case we take A is finite. Then what happens? Then every subset of a finite set is finite. Finite set is finite. Hence countable. Finite means countable. Therefore, the first case is proved. Therefore, subset of a countable set is countable. Countable set is countable. Now, second case is A is finite. Then what happens? Subset of finite set is finite. Therefore, it is countable. Case 2. Let capital A be infinite. A is finite. Capital A is infinite. Now here what happens? A infinite set may have finite subset. Again here we have two cases. If the subset of A is finite, because infinite set may have finite subset. If the subset of A is finite, then it is countable. It is countable. Now, the last case is important. The last case is, suppose A is infinite, its subset is also infinite. But we have to prove that is countable. Let capital A be infinite. Now what do you have to prove? It has a subset which is countable. Let A be infinite, but what is here? A is given as countable set, correct? A is countable. A is infinite means, countably infinite means denumerable, correct? A is infinite, denumerable set. Then what do you mean by denumerable? A can be, elements of A can be arranged in sequential order. That is the meaning of denumerable. Even though it is infinite, it is denumerable means elements can be arranged in some definite order, sequential order. Suppose A is infinite, denumerable, and A is A1, A2, A3, etc. Let capital B be a subset of A. Subset of A. What do we have to prove now? We have to prove that B is countable. B is countable. For that, B is subset of A and is infinite. That is important. First case already taken. We have taken subset of, that is A is infinite and subset of A is finite. Then it is countable. Now A is infinite, subset of A, that is B, is also infinite. Then each element of B is of the form AR. Of the form AR. Why this? Because it is the elements of A. A1, A2, A3, etc. They are arranged in sequential order. So elements of B are also of the form AR, where R is a positive integer. Positive integer. Now, what do you have to prove? B is infinite subset of A and B is also countable. B is also countable or denumerable. That you have to prove. What are elements of B? They are of the form AR, where R is a positive integer. Let now we find out elements of B. Let N1 be the least positive integer, such that N1 belongs to B. B is subset of A here. First element we will take N1 is the least positive integer for which An1 belongs to B. Then B is not only equal to An1. B is the, say we write like this, B is not equal to An1 means it is not only equal to An1. It consists of some other elements. B is not equal to An1. Then what is the next element of B? N2 be the least positive integer, such that An2 belongs to B. Then what are the elements of B? An1, An2 are elements of B, and also N2 is greater than N1. It is important. We have taken elements of B like this. B is An1, An2. B is not equal to this. B is not equal to An1, An2. What is the meaning of this? B is not only equal to An1, An2. It consists of some more element because we have taken B as infinite. Now, what are N1, N2 here? N2 is greater than N1 and B consists of An1, An2, but it is not restricted to only two elements. Some more elements are there. Now continuing like this, what do you get? B, the subset of A is of this form: An1, An2, An3 and Ank and so on. This is subset of B and it is infinite. Now I say that B is denumerable. B is denumerable. Why B is denumerable? B is denumerable and we conclude hence it is countable. Why B is denumerable? Or when we say that set is denumerable? Set B is denumerable means you have to prove that it is equivalent to n. Equivalent to n means there should exist a mapping f from n to b which is a bijection. Now what is that mapping? We define f from n to b by f of nk is equal to ank. F of k is equal to ank. K belongs to n here, any natural number. We define f of k is equal to ank. Then what happens? F of 1 is equal to an1, f of 2 is equal to an2, 3 is equal to an3. This is the correspondence. Now this is important. We define f from n to b by f of k is equal to ank. Then f is a bijection. Bijection means 1 1 as well as 1 2. F is bijection means b is denumerable. B is denumerable. Therefore, the subset of A is infinite, but it is denumerable. It is countable because it can be, there exists a mapping from f from n to b, which is defined by this f of k is equal to ank. This is a bijection. Therefore, B is denumerable. Hence, the subset of countable set is countable. See the different cases. What is the theorem? Subset of a countable set is countable. Countable set is countable. What are the different cases? We have taken first A is any countable set and B is a subset of A. A is countable set, B is a subset of A. First case is we have taken A is finite. First case, A is finite. I briefly explain once again proof of this. A is finite. Subset of a finite set is finite. Therefore, B is finite. Hence, B is countable. First case. Second case is A is infinite. Second case. If A is infinite, again there arises two cases. B may be finite. B may be finite. B may be infinite. Infinite. Again, if B is finite, subset of A is finite, then what happens? Every finite set is countable. It is countable. The last, this case is important. What is this? A is infinite set and B is infinite subset of A. But we prove that this B is countable. It is countable. How we have proved this one? We have arranged the elements of B as an1, an2, an3, etc. Therefore, there exists a mapping from M from N to B, which is bijection. Hence, B is denumerable. This is important theorem. Now, an immediate corollary to this. It is like this. Every infinite subset, every infinite set, every infinite subset of a denumerable set is denumerable. See, corollary is like this. Every infinite subset of a denumerable subset is denumerable set is denumerable. That is this case, last case. This may be separately taken as a result. Therefore, it is stated as corollary to the above theorem. Every infinite subset of a denumerable set is denumerable. That is, you have to write this proof. It is exactly same as this. Now, these results are important because we may use this to prove that some sets are countable or uncountable. Next we prove certain, we take certain sets and prove that they are countable, or we verify they are countable or uncountable. Now next one more theorem is like this. Theorem is every infinite set has a denumerable subset. What is the difference between the corollary stated and this one? Corollary was like this: every denumerable subset has, every denumerable set has, or every infinite subset of denumerable set is denumerable. Can you find out any difference between previous corollary and this one? What is the corollary? Every denumerable set, every denumerable or every infinite subset of a denumerable set is denumerable. This was the previous corollary. Now, every infinite set has a denumerable subset. See the difference here. In the previous article, we have proved that every infinite subset of a denumerable set is denumerable. But here, difference is every infinite set, it need not be denumerable. Every infinite set has a denumerable subset. But here, set is already denumerable. Every infinite subset of denumerable set is denumerable. But here set is infinite, but it has denumerable subset. Here we have not stated whether this infinite set is denumerable. That is the difference. Now how to prove this one? Every infinite subset set has denumerable subset. To prove this, let us take A is infinite set. Proof of this. Let capital A be infinite set. Let A1 belongs to A. Then, since capital A is infinite, capital A is not equal to only A1. That is the meaning of only A1. Therefore, there exists A2 belongs to A, such that A is not equal to A1, A2. It consists of some more elements. Proceeding like this, we get a subset B of A, which is equal to B subset of A, which is equal to A1, A2, A3 and so on. It is infinite. Now I claim that B is denumerable because we define a function from n to b by f of ak or f of k is equal to ak. Then what happens? This becomes a bijection because how the correspondence is there? 1, 2, 3, etc. 1 is related with A1, 2 with A2, 3 with A3, K with AK and so on. So there is 1-to-1 correspondence. So it is, this function is 1-to-1 bijection. So B is denumerable and B is infinite subset of A. Infinite subset of, it is, 1 minute, I clear this one. What is B here? B is subset of A and A is infinite and B is denumerable. Now, one more important result is this. Result is like this. We prove all these results and finally we consider some results. For example is prove that set of real numbers is not countable. Such results. Or n cross n is countable. Real numbers is not countable. Now the next theorem is like this. If f from A to B is injection 1 1, then f from 1 minute, I take this statement is like this. Now I can give only the statement of this, prove the theorem in the next video. Theorem is like this. If f from A to B is 1 1 and A is denumerable, A to B is 1 1, A is denumerable, then f of A is denumerable. F of A is denumerable. Very important result. I will explain proof of this in next video. Using this, we can prove that n cross n is countable. N cross n is countable, and this becomes, if we use this one, the proof of this n cross n is countable becomes very easy. I think all of you followed 2 theorems there. Go through once again the video. Have any difficulties, you can contact at any time. Yes, thank you.